Hi, today's topic is Diffuse-CLoC, a method that uses guided diffusion to perform physics-based character control with look-ahead planning. Physics-based character control means we generate actions that are executed by a physics simulator. The simulator enforces dynamics, context, and external forces. In this setting, we care about feasibility. The action sequence must keep the character stable and physically plausible in simulation. At the same time, interactive tasks require controllability. Examples include changing a target location, adding obstacles, specifying a path, or setting keyframes. The central goal here is not only producing realistic motion, but supporting task changes that add inference time without retraining a new policy for each task. Many recent methods use diffusion because it supports multimodal sequence generation and flexible conditioning during sampling. In physics-based character control, two families appear repeatedly. The first family is kinematic diffusion plus a physics tracker. The diffusion model outputs a kinematic plan, and the tracker attempts to reproduce it in simulation. The second family is actionally diffusion policies. The diffusion model outputs actions which are directly executed. Both families attempt to combine task conditioning with physical plausibility, but they fail in different ways, especially when constraints applied at inference time. The core limitation is distribution mismatch. The tracker policy is trained on trajectories that arise from its training data and training procedure. Its stability and performance depends on that distribution. When we apply inverse time guidance or inpainting to the kinematic diffusion model, the generated trajectory can shift away from what the tracker can reliably follow. This is not only a quality issue. Um, it is it becomes a feasibility issue. The the tracker may pursue actions that cannot keep the character stable while trying to reduce tracking error. The second issue is structural. Constraints are handled by the planner, while feasibility is handled by the tracker. If the planner outputs a trajectory that is dynamically difficult, the tracker must compensate without having been trained for the exact scenario. The practical outcome is that task constraint change can lead to unstable behavior unless guidance is done carefully, and this tuning can be task specific. Action-only diffusion directly targets feasibility because it generates the control inputs that the simulator executes. The limitation appears when we want to specify tasks. Main tasks are state-based. Um, Distance to target, collisions, and vector reaching and path following are almost naturally written as function of states over time. If we generate actions, we cannot evaluate this state-based objective until we roll out the dynamics. Inference time guidance typically needs gradients of cost with respect to the sampled variables. If the sampled variables are actions but the cost is defined on states, then the link passes through the simulator dynamics. This makes the guidance pipeline more complex, and it can reduce the convenience of changing the cost and resample that kinematic diffusion provides. Also, for tasks that require planning, it is often clearer to operate on a predicted state trajectory. Action-only generation does not represent that trajectory explicitly, so expressing look-ahead objectives can become more involved. About this, Diffuse-CLoC changed the modeling target from states only or actions only to states and actions jointly. The model generates a look-ahead trajectory that includes future states and the actions intended to realize them. This allows task constraints to remain in state space where they are easy to define. At the same time, feasibility is addressed because the model is trained to generate consistent with the generated states under the physics dynamics represented in the data. The key expectation is that inference time guidance applied to the state trajectory will also influence the action trajectory because both are part of the same joint sample. This slide explains how Diffuse-CLoC runs as a look-ahead controller and why it introduced a ruling scheme. The controller uses a receding horizon loop. At each time step, it generates a future sequence of states and actions. Executed only the first action, then replaced at the next step. Because diffusion sampling is stochastic, replanning from scratch every step can reduce temporal consistency, even when environment changes only slightly. The ruling scheme addresses this by maintaining a first-in, first-out buffer of the future plan. Each step, the buffer shifts forward and only a new far future segment is appended. That appended segment starts from a noise initialization. Denoising is applied to the buffer so that near future segmentation remains relatively stable while far future segments remain more adjustable. Practically, this supports stable execution while still allowing the plan to adapt when constraints change. When presenting, the slide focuses on what is being generated and how the denoising network is structured. Tokens are arranged by interleaving states and actions along time. A state token followed by the corresponding action token. During sampling, the future segment is represented by noise variables. The denoiser transformers takes these noise sequence and outputs the noise estimate for each token. Implementation was diffusion models typically either predict the added noise or predict the clean values. The key design choice is that states and actions are generated jointly. This is what allows state space constraints to influence the generated actions within the same sampling process. It's about attention mask, which is a key mechanism in the method. The right panel visualizes which tokens can attend to which other tokens. State tokens are allowed to attend to future state tokens. This supports global consistency of the predicted state trajectory over the horizon, which is important for planning like behavior. Action tokens use casual cursor attention. They can attend only to past and present context. The motivation is that long horizon state predictions are inherently more uncertain, and immediate actions should not depend directly on those uncertain predictions. In short, the mask explicitly separates the planning from execution within a single transformer. States aggregate look-ahead information and actions remain stable for execution. So it's about how to train model. The training dataset contains sequence of states and corresponding actions that were executed in simulation. In many setups like this, actions can be PD targets, but the key point is that actions are executable and paired with states. Training follows the standard diffusion denoising objective. Difficult diffusion step add Gaussian noise to both states and actions, then feed the noise sequence to the denoiser transformer. The model is trained to predict either the injected noise or the clean variables, and the loss minimizes the prediction error. Practical detail is how action loss is handled. Long horizon actions tend to be more uncertain, and immediate actions dominate control stability. Therefore, the loss can emphasize near-term actions, and far future actions supervision can be downweighted or masked beyond the action horizon. This focus is running on the parts that matter most for executing the receding horizon control loop. This training setup supports the main tree. Cluster depends on state, but because actions are trained jointly, guidance on states can propagate to actions within the same sampling process. It's the one of example of application. Obstacle avoidance is expressed as a cost over the future state trajectory. The environment obstacles are represented by an SDF, which provides a distance to surface value and indicates penetration when negative. A cost term penalizes states that approach obstacles too closely or penetrate them, and this cost is accumulated over the horizon. Second cost term typically puts the character toward the goal or waypoint. Guided diffusion then modifies the sampling to reduce the total cost. Because actions are part of the same joint sample, the method aims to produce actions that are compatible with the collision avoidance trajectory rather than requiring a separate tracker to compensate after the fact. Is another example, motion in between. Motion in betweening fixes the set of keyframes, then asks the model to generate the missing segments. In physics-based setting, the missing segment must be dynamically consistent and stable, not only visually smooth. In painting in diffusion constraints the time index to given values and samples the rest. Here, Here the constraints variables are keyframe states, and the unconstrained variable includes intermediate states and the actions needed to realize them. The method aims to produce the in-between segments that satisfies the keyframes and remains executable in simulation without relying on the external tracking controller to collect the logical inconsistencies. Evaluation focuses on both visibility and controllability. Visibility is measured by stability-related outcomes, failing, failure to execute actions, or inability to satisfy dynamics and contexts. Controllability is measured by task success, reaching targets, avoiding obstacles, respecting leads, respecting key frames, and meeting timing constraints. The comparisons typically includes kinematic diffusion plus tracking controls, because that is the common baseline structure for combining diffusion planning with physics execution. Key points of interest is sensitivity, whether performance changes significantly when task constraints or guidance weights are changed. The paper positions Diffusion-CLoC as improving robustness to such changes by coupling planning and execution in a single joint generator. So finally, the main message is structural. If we separate planning and execution into different modules, task constraints applied that influence time can produce plans that the tracker cannot reliably execute. If we generate only actions, state-based task constraints become more difficult to impose during sampling. Diffuse-CLoC addresses both by generating states and actions jointly, keeping task constraints in state space, and training the model to produce actions consistent with those guided state trajectories. The attention mask separates the roles of state planning and action execution, and the rolling inference mechanism stabilize the receding horizon process. The resulting system is positioned as a piece-based look-ahead control, where downstream tasks can be changed by modifying state space costs at inference time.